So we've looked at the first derivative test for a stationary point, and now we're going to look at the second derivative test. So this is a test that we're going to apply to stationary points to check if it is a local maximum, a local minimum, or a stationary point of inflection. So let's start with a quick recap of the second derivative. If I say, for example, that y is equal to x squared, if I plot that out, it looks something like this. If I differentiate y, I get dy dx is equal to 2x. That's the derivative of x squared. If I plot that out, so let's say I put x here, and I plot dy dx on that axis, and that plot is a straight line, like this. So that is a plot of 2x. It's a plot of dy dx. And if you compare the two, it kind of makes sense. Because if you look on the left side, on the negative side of the x-axis, you can see that y as a function of x is decreasing. And then it's 0 at x equal to 0. And then it's increasing on the right hand side. And then if you look at the blue line, you see it's negative on the left, it's 0 in the middle, and it's positive on the right. So that negative left side corresponds to y decreasing, and the positive on the right side corresponds to that increasing. And you can see that as you get to higher and higher values of x, if you look at that white curve, say on the right hand side, you see that the bigger value x gets, the more sharply that white curve is increasing. It gets steeper and steeper. And that corresponds to the fact that that blue line is getting higher and higher as x gets to larger values. So we can differentiate that blue line again and get the second derivative. That is d2y dx squared. And I differentiate 2x and I just get 2. So if y equals x squared, the first derivative, dy dx, is 2x. The second derivative, d2y dx squared, is 2. So I can plot out that. That's just a constant. So here's x. Here's the second derivative now on the y-axis. And if I just plot out 2 as a function of x, well, it's just a constant. It's just 2. That's what it looks like. So the second derivative is constant. So y is equal to x squared. That's a curve. This first derivative is 2x. That's a straight line as a function of x. And the second derivative is a constant. It's just 2. The reason it's a constant is because if you look at the first derivative, 2x, that's a straight line. So that has constant slope. So when you differentiate that again to get the second derivative, that comes out to be a constant. So for y equals x squared, the function is a curve, the first derivative is a straight line, and the second derivative is constant. That won't always be the case. If you had a more complicated function, you wouldn't be guaranteed to have a straight line for your first derivative or a constant for the second derivative. But when you have a local minimum like this, what you are guaranteed, if it's a local minimum, is that to the left of your stationary point, your first derivative will be negative, it will be 0 at the point, because that's the definition of a stationary point, and it will be positive on the right of your point. That's for a local minimum like this. So if your first derivative is going from negative to 0 to positive as you go through your stationary point, your second derivative is guaranteed to be positive. So if I have a function y equals f of x, a point x1, y1 is a local minimum if the first derivative is 0 at that point, meaning it's a stationary point, and also the second derivative is positive or greater than 0 at that point. So if I have both of those conditions, then I know that I have a local minimum. That's the second derivative test. So what if the second derivative was less than 0? In that case, we would get a local maximum. Let's say that y is equal to minus x squared. For example, I get a function that looks like this. The first derivative is now minus 2x. If I plot that, put dy dx up here and x here, minus 2x looks like this. You can see that that white curve on the top is increasing on the left, so the green curve is positive. It goes to 0, where it goes flat there in the middle, and on the right side the white curve is decreasing, so the green curve, or the rate of change, must be negative. Since the green curve is going from positive to 0 to negative, I expect the second derivative, or the rate of change of that green curve, to be negative. If I calculate the second derivative, I differentiate minus 2x and get minus 2. So that's a constant, and it's negative. So if we go back and look, what we have here is a local maximum at this point here, x equal to 0. And we can see that the first derivative, because the white curve is going up on the left, 0 in the middle and down on the right, the first derivative is positive, then 0, then negative. Positive here, 0 here, and negative here. So the rate of change of that green curve is negative because it's decreasing. Positive to 0 to negative, it's decreasing, so its rate of change is negative. That green line there has a negative slope. So I get the third derivative and I get something negative. So I'll check, it happens to be a constant here, but in general what I'll have to do is check. The point I'm interested in here is x equal to 0. So I check x equal to 0 here, and I find that my second derivative is negative at that point. And since I have a stationary point and a negative second derivative, I can confidently say that what I have here is a local maximum. So my second derivative test says that for y equal to f of x, a point x1, y1 is a local maximum if it's a stationary point where dy dx is 0, and that at that point the second derivative is negative or less than 0. So we've looked at positive second derivative and negative second derivative. There's only one possibility left, and that's if the second derivative turns out to be exactly 0. If at our point x1, y1 we have a stationary point, but the second derivative is actually equal to 0, and the second derivative actually changes sign as we pass through x1, then we have what we call a stationary point of inflection. If we have the second derivative changing sign through x1, but it's not a stationary point, that's an ordinary point of inflection. So an ordinary point of inflection is somewhere where we change sign in the second derivative. It looks something like this. An ordinary point of inflection will be somewhere where the second derivative is going one way and then the second derivative is going the other way. So you see on the left there of that yellow curve, that would be a negative second derivative. And on the right, that would be a positive second derivative. You see how it's getting steeper and steeper. So the first derivative is getting bigger and bigger. So the second derivative must be positive. So you see somewhere in the middle there, we change from a negative second derivative to a positive second derivative. And we get our point of inflection there. That is where the second derivative is 0 and it's changing sign as you go from the left through to the right. The stationary point of inflection will be something similar, except that your first derivative will actually go to 0. So if I come up here in a curve, I actually go to 0 and then I come back up. Right here is a stationary point of inflection. Whereas the one on the left there, if it doesn't go to 0, say there's a positive slope here, that's an ordinary point of inflection. If the second derivative goes to 0 but it doesn't change sign, that's a case we just won't worry about for the moment. We're only interested in the cases where the second derivative changes sign as it goes through 0. And that's either an ordinary point of inflection or a stationary point of inflection. If you look at the back of exercise sheet 4, there's a summary of all this and in what case you get what kind of a stationary point. The last thing I want to talk about are absolute maximum and minimum values. So far we've looked at local maximum and local minimum values, where it's the biggest or smallest value in its immediate neighbourhood. But what if we want the absolute maximum value of a function? Well, that point is going to be at some stationary point, or at the end point if we have some restricted domain. But I want to look at two cases first. If I have a function like this with only one stationary point, then and it's a local maximum, then it must be the absolute maximum. The reason being that if there's only one stationary point, that's the only place that your function can turn around. So you might say, well, if this red point is local maximum, how do I know the function doesn't get higher than that somewhere else? And the reason is, if there's only one stationary point, then this just has to keep on going down and down and down either side. Because if it were to turn around, that would be a second stationary point. And similarly, for a local minimum, if I have one stationary point on a function, and it's a minimum, or a local minimum, then that must be the absolute minimum value that function takes anywhere. If I had, let's say, 3 stationary points, let's say I calculate a stationary point here, here, and here. And I know that that first one was a maximum, so it was a bit like this. The second one was a minimum, and the third was a maximum. Let's say I did my second derivative test. I know they would join up something like this. And if those were the only 3 stationary points, then I would know that the function can't turn around anywhere outside there. So it has to keep going down here on the right and keep going down here on the left. And if I wanted the absolute maximum here, well, then I know it's going to be here. Because this one is bigger than this one, which is my other candidate for the maximum. And there can't be a higher point anywhere outside that, because these are the only stationary points that I have. So the absolute maximum would be right here. There wouldn't be an absolute minimum, because the function looks like it just gets lower and lower and lower. So that's how you can use stationary points and the second derivative test to find out what kind of stationary points they are, and thereby find the overall greatest or least values that a function takes. So if that's a bit confusing, don't worry, because the next thing we'll do will be a few examples of this, but that will be the next video.